In our previous lecture, we have studied surge phenomenon in power transformers, part 1. So, this is surge phenomenon in power transformers, part 2, an extension of the previous lecture. So, the equivalent circuit we have seen here. The last time we have seen that it is capacitive network when time t is equal to 0. So, when immediately after the wave is impinged here, or just like switch on or something like that, or any transient wave coming here. So the circuit equivalent is a capacitive circuit, distributed capacitive circuit equivalent, and we have also seen the voltage distribution in both grounded neutral case and open neutral case. Now for the present we see the equivalent capacitance grounded neutral case. Now a transformer winding is not an infinite line. So there's a number of reflections occur here. So this is of course initial voltage distribution we have seen, but that is just at t is equal to 0 instant. After that what will happen? So that need to be investigated. There may be several reflections also. There may be a wave phenomena. The wave may go here and then again get reflections like that. So therefore, for further equivalent circuit, we have to obtain or the equation or how the voltage distribution will change, that need to be found. So to find the equivalent capacitance, we find the energy stored in one section and integrate it over the length and then equate it to the energy stored in the equivalent capacitance, which is the total energy in the system is half into C V square, half C V square, C Eq. This is the equivalent capacitance of the system or the winding. Now this is total energy. So if CS and CG represents the total series and ground capacitances, means this is total series capacitance is CS. Total ground capacitance means shunt capacitance is CG. If that is there, then this is per section, right? KS, KG. So Ks can be expressed as Cs by delta x and Kg can be expressed as Cg into delta x. What is delta x? What is x actually? X equals to 0 is G at G or N position, and x equal to 1 is this portion. It means this is per unit distance. Delta x is per unit distance. Y is actual distance actually from here to here. So per unit distance, if x is per unit distance, its maximum value is 1 only. 1 unit only, and its minimum value is 0 here. So this is how the capacitances are having the relationship. This we have seen in our previous class. So the total energy stored, the energy stored in the series capacitance in one section is DES. So in the series capacitance, one section differential energy in one section equals to half that section capacitance into voltage across that series capacitor is delta V. So squaring this one, half CS by delta x, replace KS by CS by delta x into delta V square again, and CS, this delta x remove and then put it below this one, that half CS into delta V by delta x whole square into delta x you can write. So the delta x, since it is squared here, again here delta x will come into picture here. Therefore, DES equals to half CS dou V by dou x, partial derivative, dou V by dou x whole square into dx. We have Vx equals to V by sin h alpha into sin h alpha x. Already we have determined for grounded neutral case. So, dou V by dou x, differentiating this, V by sin h alpha x into alpha into cos h alpha x, derivative of this sin h alpha x. Now, thus, differential energy is in series capacitor is one section is half Cs alpha square V square sin h square alpha into cos h square alpha x dx, where alpha is equals to root of Cg by Cs. Similarly, the energy stored in the ground capacitance in one section is Deg equals to half Kg V square half Cg delta x into V square. Now here, this upon simplification, Deg equals to half Cg V square by sin h square alpha x into dx. So this will become like this. Now here alpha is equal to Cg by Cs if you substitute in this equation. This term, this initial term will be same as this term, if you can see. Only this cos h square alpha x and sin h square alpha will be different. Here it is cos h square alpha x, here it is sin h square alpha x. But this term is same. You can see here, this term also. Because alpha square means this will be square, and then CS gets cancelled, CG will remain here. Therefore, the total energy stored in one section is DES plus DEG. So, which upon substitution from the previous section and then simplification using this relation, so it becomes DE equals to half CG V square by sin h square alpha cos h2 alpha x into dx. Now, this we need to integrate for all the sections from 0 to x, right? 0 to 1. For x is 1 means complete winding. So, EA equals to integration of 0 to 1 half CG and this term total energy term, and then this becomes after integration and then substitution of this, then it becomes 1 by 2 alpha CG V square cot h alpha. This can be further simplified actually. Alpha you can use this value and substitute here, and then upon final simplification we will get E equals to half into this portion into V square. This portion is CEQ then, because this is total energy, half CEQ V square. Therefore, CEQ is equal to root of CS into CG into cot h alpha, or alpha also if you substitute in terms of CG and CS, CQ equals to root of CS CG cot h root of CG by CS. So, this is how the total equivalent capacitance can be obtained in terms of CG and CS for grounded neutral case. This is grounded neutral case. But similarly, that open or isolated neutral case also, if we simplify, instead of cot h, we will get a tan h. That is the only difference. You can do that simplification and then see. So, in this case, the neutral is not grounded, but it is open or isolated neutral. So, this is how the equivalent capacitance will turn out to be in that case. Next, introduction of self inductances into the circuit. Now, the capacitive circuit is valid only for initial distribution. After t is equal to 0, slowly the inductances will also come into picture. So, inductive current, inductive reactance, will become finite, and then thus the circuit assumes the form of oscillatory LC network. So, the inductances will be in parallel with this series capacitances. So, here it is indicated with small capital L dx, where each section inductance is divided into n. This is divided into n sections, and total series inductance is divided into n sections. So, considering a single layer transformer winding, only the self inductances are dominant. So, this is having only one layer in one winding. So, primary and secondary also there is no mutual inductances. Here that are not considered, and in the same winding also only one layer we are considering. So, one layer single winding. So, single winding means just there are no two layers in the same winding. So, but that is for simplification we are considering that one. So, the mutual effects, ignoring the mutual effects, this is how the self inductances. Actually, of course, self inductances are very dominant. And then this is how the equivalent circuit will look like. Now, the objective is to find out a function f of v comma x comma t equals to 0, and then obtain a solution for this kind of circuit. So, we have I equals to IL plus IC, because inductive current plus capacitive current both have come into picture. And here delta I will be going through this capacitances. This voltage is small v. This voltage here, this node voltage is small v. The voltage across this branch is small delta v. So, this is how differential elements are taken, and then delta v equals to, delta v means this delta v equals to L delta x into dou IL by dou t, that IL through the current through the inductor. This is inductor relationship. And then similarly capacitor relationship of series winding, and then similarly the capacitor relationship of the shunt winding. Using these three, and then rewriting the partial in terms of partial derivatives. So IC becomes from 5. IC becomes CS into dou by dou x into dou v by dou t, or CS into dou square v by dou x dou t. Similarly, 4 can also be rewritten. Equation 4 can also be rewritten. Dou v by dou x equals to L into dou IL by dou t. And from 6, again from 6, this equation we can rewrite into dou I by dou x equals to Cg into dou v by dou t. So upon these simplifications, you go through these, and then differentiating with respect to x sometimes, t sometimes, and then finally we will obtain this equation dou square v by dou x square plus LCS into dou to the power of 4 v by dou x square dou t square minus LCG dou square v by dou t square, which is a function of v comma x comma t equals to 0. So this can be solved for v of x comma t. Here dou v by dou t is a dou by dou t is a is an operator which can be replaced by p. So this is done in the next actually. So dou by dou t equals to p. This is actually frequency related term. So we will replace it by j omega later. But for the time being replace it by p. So if you replace it by p, this equation becomes this equation dou square v by dou x square plus p square into this, and then Lg p square into v equals to 0. Or taking common this dou square v by dou x square, you will get in terms of this one. Again, then p square can be replaced again by dou square v by dou t square. So this equation relates time rate of variation of voltage into the space rate of voltage variation. Of course, p square is there, this operator. This is a frequency dependent term here. So this is how the time rate is related to space rate here. And the above equation represents the equation of a one-dimensional traveling wave. You might have heard it on transmission line there. The voltage travels like a wave, right? Similarly, here also this is a traveling wave, whose solution may be obtained by appropriate integration techniques. Now, one of the solutions for this is f of x plus ut equals to 0, where u is the speed of the traveling wave. So we get, for example, the differentiate 2 times with respect to x, you will obtain f double dash x plus ut. D square dou square f by dou x square is equal to f double dash x plus ut. Similarly, differentiate 2 times with respect to t, you will get u square into f double dash x plus ut. So then we can write this is f double dash x plus ut. So comparing two differentiations here, dou square v by dou t square and dou square f by dou x square, both comparing both of them, you can write dou square f by dou x square equals to 1 by u square into dou square f by dou t square. This is the final relationship, and compare this relationship with our equation, then obtain what is the relation between propagation velocity u and this one. So the u can be written as root of 1 plus LCS p square by LCG. This is the velocity at which the voltage wave travels. Now obviously the voltage wave depends on the frequency of the frequency of the applied voltage. So the velocity of propagation of a particular wave is dependent on its frequency. So this is important. So let us replace that term by, of course, after some simplification like this, and replace the dou by dou t by p by j omega. So if you replace the p by j omega, it becomes u becomes 1 by LCG plus j omega whole square by alpha square, or minus omega square by alpha square. Alpha again Cg by Cs, if you root Cg by Cs if you substitute, then it becomes like this, and then further simplification can be done. So taking out 1 by LCG common, so here you can see 1 minus omega square by 1 by root of LCS whole square. This is again a frequency term. Let us define it as omega n. So U equals to root of 1 by LCG 1 minus omega by omega n whole square. In fact, omega n is defined as supercritical frequency. So this is important in that way. So when particular different values of omega n, we will see omega, different values of omega, what will happen to this velocity of propagation, we will see now. So if the interturn series capacitance is 0, suppose there is no interturn series capacitance, of course it is an ideal condition. So then the wave velocity is independent of the frequency because U becomes simply 1 by root LCG. This is omega c, critical frequency. Some critical, this value. So if the interturn capacitance is not present, then the wave travels with a constant velocity irrespective of the frequency of the applied voltage. So it will travel with the same velocity. So but there are different cases now. Now here this is the equation of velocity here, and then for omega less than omega n, in this case this quantity is less than 1, and then therefore this entire quantity is positive. In that case U is also real, and thus it represents a true traveling wave. It's actually a real traveling wave. These frequencies omega less than omega n are also known as subcritical frequencies. So since the incident surge voltage usually contains a large number of frequencies like this, surge voltage, like this, I have given a pulse here. Of course, standard impulse will have fast rising voltage and then slow decay of the voltage. So such voltages, what will happen? So they contain different frequencies in them. So therefore, they will travel with a different velocity. Therefore, ultimately the wave becomes like this. It disperses. So it's this kind of propagation is a dispersive propagation, dispersive wave propagation. So that's what it will result if omega less than omega n. Omega is the frequency of the impinging wave. And then case 2, omega equals to omega n. Omega equals to omega n means this quantity becomes 1, and then inside the root it becomes 0. Therefore, U becomes 0. Therefore, there is no wave propagation in this case at all. If omega is exactly equals to omega n, in this case there is no wave propagation. So then omega more than omega n. In this case, then this quantity becomes imaginary and the wave does not propagate. Therefore, this case corresponds to a standing voltage wave, standing wave phenomenon will occur. So these three types of wave phenomenon will occur in the transformer winding if different frequency waveforms are applied to the transformer winding. So different surges appear on the transformer winding. So analysis by circuit theory for subcritical frequencies. Now subcritical frequencies where subcritical frequencies means a real traveling wave will be there. So in this case, what is the equivalent circuit? So that can be derived here with some little bit calculations. So if for subcritical frequencies omega by omega n less than 1, so where the velocity U is real, thus representing a true traveling wave. The frequencies are lower than the supercritical frequency, omega n is equal to 1 by root LCS. Now this is the equivalent circuit. LDX you consider series inductance also in the circuit, which is in parallel with the series capacitances. So this is how the equivalent circuit will look like. Now considering parallel branch in a section consisting of series self-inductance of the winding and the interturn series capacitance like this. So assuming this is Z delta X. So now equivalent impedance can be found using this formula. And upon a little simplification, you can show that it becomes j omega into L by 1 minus omega by omega n whole square. So this quantity is a frequency dependent inductance can be introduced into the system. So the capacitance can be replaced, ignored or removed the circuit analysis, and then a frequency dependent inductance can be introduced into the system like this. So Z delta X is equal to J omega L dash into delta X. So this is one simplification procedure for circuit theory, but this is valid only for subcritical frequencies where omega is less than omega n. So thus for the surge voltages occurring at subcritical frequencies, the parallel LC branch in the equivalent circuit may be replaced by equivalent inductors L dash delta X, which are frequency dependent inductances in each section. Okay, thank you.